what we're doing is simply identifying whether a function is linear or nonlinear, and we're going to look at three different things. We're going to look at graphs, and look at a graph and say whether something is linear or nonlinear. We're going to look at equations and see whether something is linear or nonlinear. And then we're going to look at tables. Now, the first one of those is a graph. Like I said, this is a little bit easier. How do you think we determine from a graph whether something is linear or nonlinear? Oh. That's direct variation. We don't have to do, it doesn't have to have direct variation in order to be linear.
Well, when your equation is like a straight line, endless, and nonlinear equation would have like different points that are at which line.
Okay, yeah, I mean, it's kind of in the name. We have a linear, which would mean it is a line, and lines in the mathematical definition of a line, it has to be straight, right? Okay, so anything that is not a straight line on a graph would be, yeah, how tough is that, right? Straight line, linear, not a straight line, not linear. Piece of cake, right? All right, now let's talk about an equation. Now, the advantage to an equation is we already know a little bit about linear equations. What do linear equations look like? What does just a typical linear equation look like?
Slope and y-intercept.
Okay, so that would be
Y equals mx plus b.
X plus b.
right? That's the most common way that we're used to working with a linear equation, right? And, that's kind of what we worked towards from early on in the unit when we were just putting in that form just to put it in a t-table to later in the unit where we were using that to get slope and y-intercept. So this is what a linear equation looks like. So if you want to find out whether something is a linear equation or a nonlinear equation, all you have to do is find out if you can rewrite it that way. Okay, for instance, let's say I have an equation let's say I have this equation here. If we want to find out whether or not this is a linear equation, all I have to do is try and solve for y. So if I want to solve for y, what's the first thing I need to do here? Get rid of the 3x, and since it's positive, that means I should subtract it. So I get positive 4y equals negative 3x plus 2. Then what do I need to do next? What's my goal? Okay, why?
Because you need y by itself.
Okay, remember, we're solving for y, which means we need y by itself. What's in the way of me having y by itself? 4. So that's what I need to get rid of, right? And since I am multiplying by 4, that means I need to divide by 4. So on the left-hand side, I get y, and on the right-hand side, I get negative 3/4 x plus 2/4, or 1/2 if you reduce it. Is that in y equals mx plus b form? Yeah. We have a y-intercept of 1/2, and we have a slope of negative 3/4. This is in our slope-intercept form. So this one we can say is linear. We don't have to worry about graphing it. All we have to do is figure out whether or not it's linear. So what about if I have this? Now what's my goal?
Dividing.
What's our goal? Remember, what do we want?
Slope-intercept.
We want slope-intercept form, so we want y equals. So we need to get rid of everything that is on the same side as y, which means what do I need to get rid of first? That thing. And since it's positive, that means we can subtract it. It's just a number. We don't know what number it is. I mean, x could be 1 and that could be 3. X could be 2 and that could be 3 halves. We don't know. But whatever it is, it's still a number. You can treat it like a number. Don't get scared just because it's a fraction with a variable on the bottom. Okay? It's still a number, which means I can add it, subtract it, all the stuff I can do with any other number. So I'm going to subtract 3 over x from both sides, and I get 2y equals negative 3 over x plus 4. Now what do I need to do? Divide by 2. So I get y equals, and now this one is going to be negative 3 over 2x. Because the 2 gets added to the bottom because we're dividing. So we get that. Plus 2 if I divide 4 by 2. Is that y equals mx plus b form? Nope. Because where's my x? Am I multiplying 3 halves by x? Nope. I'm multiplying 3 halves by 1 over x. Right? Because if it was multiplied by x, x would be on the top or out in front of it. This is not being multiplied by x. So this is nonlinear. So, in order to check whether an equation is linear or nonlinear, you're going to need to solve it for y. If you get y equals a number times x, it can be a fractional number, but a number times x plus or minus some other number, then it's linear. If you get anything else, when you have y all by itself on the left side, if you have anything other than mx plus b on the right-hand side, then that means it's nonlinear. All right, and then the last thing we can look at is a table. All right, so if I'm given a table, what do we know about a linear equation that you could look at a table and determine whether or not it's linear? Exactly. Okay, if it's a linear equation, then it's going to have the same rate of change. In other words, the slope between any of its 2 points is going to be the same, right? So if I find this changes by 5 and this changes by 2, which means its slope is 5/2, right? And if I come down to the next one, this also changes by 5, and this also changes by 2, which means this slope is 5/2. Now if I added another point on here, let's say I added this point. Now this increases by 10, but over here it increases by 4, which is 10/4, which is also 5/2, right? So this would be an example of something that is linear, because the rate of change between any of the points on that table are the same, right? Now, if I give you another one, now here, what does that change by? It increases by 4 as this increases by 1. So the slope there would be 4/1 or 4, right? This changes by 8 as this changes by 1. So this has a slope of 8/1 or 8. You don't have to even check any of the other points. If you find 2 points that don't have the same slope, then right away you know this is nonlinear. So, the 3 things that you're going to be looking at is looking at a graph. And if you can't tell the difference between a nonlinear and a linear graph, then we probably need to demote you back to like 2nd grade at least, I think. Right? If you can't tell the difference between a straight line and a curvy line. Yes, 2nd grade? Maybe lower? I'm not real sure. When first, you think first is when you learn how to tell the difference between a straight line and a not straight line? Okay. I know my kindergartner probably could tell the difference, but she can't draw a real straight line, so she might get confused about it. I'm not sure. But I figure that at very least by 2nd grade, we should be able to tell the difference between a straight line and a not straight line, right? So those should be easy. Okay? So straight equals linear because it's a line. Not straight equals not linear, right? Okay, then you have to be able to determine from an equation, which means try and put it in that y equals form. And then you need to know how to find it from a table, which means find the slope, find the rate of change between all the different sets of points. If they're all the same, it's linear. If any of them is different, nonlinear. Yes, Stelson.
So, how do you know that it's nonlinear? Unless you use the formula.
Because the rate of change between this point, 2, 4, and 3, 8 was an increase of 4, right? So in one, over the change of distance of 1x, it went up by 4. But then the next one, over the next increase of 1, it went up by 8. So the rate of change was much steeper, so it can't be a straight line. Remember, straight line, the slope, the rate of change is going to be the same. So if it goes over 1 up 4, it's going to go over 1 up 4. But this one's going over 1 up 4, then over 1 and up 8. So it has a different slope. So if the slope's not the same between any 2 points, then it's going to be nonlinear. All right.